Good afternoon, ladies and gentlemen. Welcome to the London Loft. Thank you for attending this session on, as it says, fraud detection and machine learning on AWS. So my name is Andrew Kane. I'm one of the SAs working out of the London office. So fraud detection is really all about, sounds obvious, trying to spot fraud in financial transactions. It's a big problem, obviously. It's a very serious concern for any bank and any financial institution, because fraud is obviously very, very attractive to criminals, because there's often an immediate reward for their actions. A very simple, quick fraud can net a few £100 here, a few £100 there, and with a large global concerted action, it can be a few £1,000,000 every day or two for a reasonably, decently competent criminal gang. So banks are under constant attack from bad actors all over the world, as you can probably imagine, trying to penetrate their defences. And they're trying to use any sort of nefarious means they can think of to try and get past different things, whether it's the card, the person, the terminal device, the store itself, multiple channels, perhaps your third-party vendors that do your backed IP transactions. They'll use any means they possibly can to try and get into you. So banks have to detect fraud, they have to prevent the fraud, but they have to do this in such a way that ordinary consumers, such as, well, the vast majority of the population, and hopefully all of you, can actually go about their normal daily business without getting blocked. But the scale of the problem is quite big. So you look across the USA a couple of years ago, 2015, the figures basically say it was in the region of $8.5 billion of fraud losses just for that kind of thing, which is not good. Globally, it went up to over 21 billion. Again, that's quite a lot of fraud. And they say it's just going to get worse. 2020 projection is over 30 billion. And this does actually sound quite a conservative estimate. I think it's going to be a lot more than that unless people start taking fraud detection seriously. So we talked to our customers about this because they're quite concerned. And they work in lots of different areas. They could work in credit card transactions. They could work in debit card, electronic transfers. They could be dealing with checks. Checks still exist. It's a great opportunity for fraud still. That's why banks are trying to get rid of them. And they also provide these services over multiple endpoints. It's not just your ATMs. It's not just your bank cards. It's not just your store terminals. It could be mobile phone apps. It could be a website presence. All these things are valid channels for the criminals to actually try and attack you. And when there are multiple channels, well, the attacks get that bit more complex and a bit more interesting. So you look at the different layers that we have. There are 5 in total. The first one is really just the endpoint problem. So it's a stolen card. Someone's compromised the ATM. They put some devices on the card reader, and they're trying to get at you that way. Really simplistic fraud attempts, but unfortunately, they work for a short period of time. They're probably one of the easier ones to actually detect once these systems are up and running, though, but they still get quite a lot of money from a fraud perspective. The second one is session-based. Now, when you log into your online banking, like I do most days of the week, I will log in, check my balance, I'll look at some of my recent transactions to make sure nothing weird has happened. I'll go to my online payments, do a quick transfer to someone, and log off. Well, that's kind of normal. That's what everyone does. What you'll find that the criminal bots will, or the criminal gangs will do the right bots to go and attack your bank. They will log in, and straight away, they'll go out and try and do a transfer, log out. So obviously that's quite suspicious behaviour, and it's something that can be tracked. But at that point, they've got your password, they've got your credentials, they're kind of in, and they're trying to sort of hijack your session to get as much information as possible, or as much money as possible. But it's not just one of your accounts. It could be doing this across multiple channels. It could be in your credit card account that you have with one bank. That could link to your mortgage account with the same bank because the deal was so sweet. That could go to a savings account and your ISA. And once they're into one, they're across all the channels. And they can start manipulating accounts or manipulating transactions to go from one to the other, cross your different accounts, and then eventually pop out of the system into their accounts. That's harder to spot. Fraudsters might also be going across multiple channels. So just stop at that one. Now, level 5, this is where fraudsters start to collude together. They start to get involved by doing a certain attack in one country in one way, another attack in a different country another way, all trying to get together to try and do a really complicated way of getting your money, which is, after all they're really after. So as the attacks go from level 1 all the way down to layer 5, it actually gets more and more complex in terms of fraud. It gets harder and harder to actually try and detect it, and therefore the resources required to try and actually prevent it become much harder. So quick show of hands, how many of you are actually running fraud detection systems today in the room? Oh, 1 or 2 lone hands. Is it a rule-based system, may I ask? Do you know? It is a rule-based system. This is quite common. It's pretty much the norm. So in a credit card environment, the workflow is something like this. A credit card transaction comes in. it will go through a simple rows engine, and these multiple rows will get checked one after the other, and at the end of it, you'll get an approval request from the bank, or you'll get a deny going back. So they'll check things like, is the card stolen? Is the store terminal one that you know is compromised? Are you over your spending limits? Is it a very strange spending pattern? Have you spent 3 years buying stuff just in London, and then 2 hours later, you're buying something in San Francisco, and they block your card? So these sort of things are all the things you check for. And they work, but they actually fall quite short. They can't do as much as you want them to do. So why do they fall short? Well, one of the obvious things is, to write the rule in the first place, someone has to have gotten into your account. Someone has to have compromised you. They've already got some money out of it. So you're retrospectively fixing this particular rule to make sure it doesn't happen again. But quite quickly, the criminals are smart. They realize these things are not working anymore. They change the attack. They move on to a different approach. You have to do a different rule, and another rule, and another rule, and another rule. So the rules themselves stay quite static. You just keep creating more and more. And if you're doing a multi-layer fraud detection, this gets a bit more complicated because it gets much harder to actually even think, how do I do a 5-layer fraud check at once? It's really hard to get your mind around it. Also, the biggest problem with these things, they are created by humans, people. We are well known for being biased in how we understand things and how we interpret things. If you have an analyst or data scientist say, this rule has to get implemented tomorrow, here it is, here's a spec, the developer will look at it and think, yeah, I know what that means, I'll implement it like this. And then a tester will look at the spec and think, I think I know what that means, I'll test it like this. And it gets released. And it doesn't always match what the data scientist meant to do in the first place, because we're just human, unfortunately. And also the fact it's human, it does mean it's written down somewhere. So gangs have been known to actually steal the rule requirements from companies just so they can get around them because they know what the rules are. So these things can leak out because, unfortunately, we're human. They're hard to manage. You have to update them. You have to update them, I won't say every day, but very frequently. So you have to feed them, water them, look after them, care for them. And that's an effort. And if you don't update them regularly, then attacks start getting through again, and you're no better off than you were last week. And it doesn't scale. This is a real problem. If you look through all 5 layers of the attacks that you can actually get, the fraud difficult for detection is really, really hard. So layer 1, it's easy, it's an endpoint. Layer 5, it's multiple accounts, multiple sessions, multiple people, multiple geos, and it gets much harder to think of the rule. So when you're trying to do it at scale, it's just difficult. And scale is also in terms of transactions. So you might get a few million transactions a day, maybe 10, 50 million at a reasonable small-sized bank. Get to Black Friday, Cyber Monday, Boxing Day sales. That's going to go up 3, 4, 5 times at least. And your system has to scale with that as well. Not just your rules across the layers, your actual system for doing detection. So we have some problems. So we talk to our banking customers thinking, well, we don't know the answers. We ask the banks, what is the problem? What things do you actually need for us to implement for you or to help you implement to make fraud kind of go away? So, first one, billions of transactions per day. A big global bank will easily get through 1 billion in a day. That's a lot. So if you want to try and process these things every single day, that's a large system, not just in terms of data storage, data processing, it's also bandwidth, machine requirements, processing power, and it's just a lot to get that stuff through every single day. Make decisions in milliseconds. This is quite hard. The banks want to detect fraud in line. It's no good someone going into a shop, swiping the card, gets the approval process, and as the person walks out of the shop with a few large 4K TVs, they say, come back, it's been declined. It's too late. The money's gone. The fraud's happened. These things have to happen very, very fast. So discussions with our major banks, they reckon the window of opportunity for this inline detection is about 60 milliseconds. That's not a lot. You want to do a very complex SQL query, it's not going to come back in time. You just cannot just think of it in that sort of way anymore. You can't just use that kind of system. It will not work. Now, of course, if you're doing batch transactions overnight, that's fine. The latency requirements is much slower. You can be seconds if you like. It doesn't really matter. But it's the inline fraud transactions for credit cards. That's what they're trying to get at. Banks have a lot of data about you all. You might not like it, but they do. So they'll have hundreds of terabytes. It's not unusual. Petabytes is becoming the new norm on the data they have on every one of us. Basically on our spending patterns, our habits, where we go, how fast we spend, what transactions we kind of use, what the amounts are we tend to use. They know all this stuff. And because they know all this information, they have to make that part of their training data for their fraud detection system. And if you don't handle all that data, hundreds of petabytes essentially, you can't do an adequate fraud detection system. You just can't do it. Compliance. Well, banks have this slight compliance issue, shall we say. So if you're dealing with credit cards, PCI DSS springs to mind. You have to comply with all of those. And so every aspect of your solution on AWS has to be PCI DSS compliant. It has to meet or exceed everything. Now, Now, that's not an issue with AWS. If you deploy this sort of system on-premise, you have the same problem. You put it on any other provider, you have the same problem. PSI DSS has to be at the sort of core of your thinking, that if you can't meet that compliance regime in your application, it's not going to get to go live. It's not going to be approved by InfoSec. So this has to be core to your thinking, as does cost. Banks basically say to us that the cost per transaction has to be as low as possible. If we're doing $1 billion per day, and the transaction cost is so high that the system for detection and mitigation costs as much as the fraud we've lost or we're going to lose, what's the point? And there are examples out there of people who have bought systems for multi-million dollars to actually implement fraud detection and realized it's just about coming close to what they lost in the first place. Why did we bother? So if you're going to spend that sort of sum of money on a fraud detection system, really be careful and think about what's the cost per transaction, because that really is quite key. And know what you're losing, or what you think you're losing. Because if it's too much, you are wasting your time. It's got to be flexible and adaptable. So the solution really has to work at all 5 layers. You can't start building out lots of different models for lots of different layers, because it just gets exponentially bigger in terms of cost, storage requirements, bandwidth requirements, etc. You've got too many things going at once. So having one good model that can handle them all with lots of instantly intelligent rules, shall we say, is probably the best way of doing these things. And also, it's got to be adaptable to the data sources you're getting, because one day you're taking feeds from 3 or 4 different data processors, the next day you take feeds from different processors. Then you may acquire another subsidiary bank from somewhere else, you've got another big bunch of historical data. Brilliant, let's train the models on that too. So you have to keep adapting and moving forward. The day you have a model, it's good for that day, essentially. You've got to keep looking for more data, keep feeding it, keep training it, keep evolving it. Otherwise, you're basically standing still. Agile and scalable, of course, we scale about all of our services on AWS. Again, Black Friday, Boxing Day, Cyber Monday, Spring to Bite, as if data volumes go up 4, 5, 10 times potentially. So you have to be able to handle that sort of volume and that sort of scale. Come January, everything goes quiet until the next set of sales come around, spring sales, summer sales, and you get some more peaks. So you don't want a big system that then sits idle for 9 months, 10 months over the year. You have to be able to scale up and scale down, which is where the cloud platform really excels. In terms of agility, in this one, we're actually really talking about data scientists. Now, data scientists are usually very clever folk. They've got a lot of good knowledge behind them about looking at data, data mining, finding out what transactions look good, what looks bad, how to build out all these rules. So they've got to be able to handle all these large amounts of data properly. So the worst thing you can do with them is have them spend half the time looking at infrastructure, looking at clusters for things like Hadoop, actually looking at the infrastructure. They don't really care. It's not really what their role's for. They're there to look at data. They want to look at data 24/7. Well, that's not quite legal. Okay, let's say 5 days a week, 10 hours a day, a bit more sane. And looking at the ML models they're building, they're defining, and each day verifying the models are still true, that they're still up to the actual mark. Anything we can do to take away the really boring heavy lifting of just building servers, who cares? They're not interested. And actually get them to do the job that they're trained for, you'll get more out of the data scientists. Just by that, you'll get better models, one hopes. Overview of machine learning. How many of you are actually familiar with machine learning as a concept or as a theory? Hopefully a few more of you. Oh, thank God. Right, so I'll give you a very, very quick overview. I will apologize in advance. This is very simplistic. I could spend hours basically talking about machine learning and neural nets. We really don't have time. So we'll keep it really simple. And the simplest way of saying it, it's basically an act of using a machine to predict outcomes based on a variety of inputs that you give it. So you basically have some sort of machine which has got lots of inputs that are controlling that machine, and depending what the inputs are, you'll get some response. Hopefully the chap will eat some soup and won't cover himself in hot liquid and burn himself to death. But to many people, neural nets look like magic because they've got no idea what's happening under the hood. They don't really understand how it works or even why it works. So how it really works is you give the artificial intelligent type machine, the Einstein machine, it looks at various items in its input, and it thinks with all its logic and all its rules it's built up behind the scenes. And all the input items are called usually attributes or features, depending on your mindset. So it looks at all the inputs and decides, I think this output should be X. I think, brilliant. And it does the output, which is X, and hopefully that's the right result, fraud or no fraud. How does it do it? Well, you have to give it a lot of inputs. And we mean an awful lot of inputs. So thousands is probably not enough. We're talking millions and millions of example input data so it can actually realize, oh, I know what fraud now looks like. It's got more of an idea of the pattern behind the scenes. So there's 2 types of main learning that are really involved in day-to-day use these days. There's supervised learning, which is one we're going to talk about more. And there's also deep learning and unsupervised learning. And we're not going to cover that because, bizarrely, fraud detection fits really nicely into supervised learning because banks have got these petabytes or even exabytes of data where they have known inputs from everywhere. And they know it was fraudulent or not, because it was fraudulent or not. It's really that simple. They've got all the empirical evidence. This transaction was good, these 10 were bad. So with that sort of data set, that's what supervised learning neural net algorithms, this is what they thrive for, it's what they love, and it works really, really well. So we're using supervised learning, we keep it kind of simple. So using that supervised learning algorithm, it will hopefully work out what the output should be based on all the input data. But more importantly, if you give it all the inputs again once it's trained, it should give you all the right outputs. If you give it 10 million transactions it's never seen before, it should give you the right output, because it's looked at your input data and it's managed to generalize the trends behind the scenes of what actually meant, well, what actually constituted a fraudulent transaction. And it will find patterns and rules and logic that you may never have thought of, hopefully. There goes the theory anyway. It's really a multidisciplinary art form. It's not really an art, it's not really a science, it's one of those things. You've got to have sort of a computer science and maths background to understand how the algorithm actually works. But to actually make it learn is more of an art. It takes that experience of the data scientist to look at it, get a feel for it, look at the data, decide which of these 4,000 rows of columns of information actually is useful. Is a day of the week useful for fraud detection? Well, who knows? But maybe it is in certain store profiles in certain situations. Maybe. Let's try that model. Let's try a different model. That's where their basically training of the art comes into it. So how many of you thought we were going to be actually talking about the machine learning aspect of it today, rather than anything else? Good, because machine learning is actually the simple part of this whole process. It's not the complex bit. The hard part is actually getting your data around, thankfully. So as I said, it's not really not an art or a science. It really is both. You've got to have both things. But when the banks are looking at petabytes and exabytes of data, you've got to get that into one place. On premise, that can be hard, because can you hold a few hundred petabytes for a training algorithm? Probably not. Can you create a second or third version for some, let's say, additional model training systems? Probably not. So for that, we really look at S3. S3 is essentially built and designed to be your data lake solution anywhere in the globe, in any of our major regions. So it meets all the security requirements pretty much of PCI DSS, because basically, natively, it can handle encryption of data inside the buckets for all the objects that you're storing in the buckets, and it can handle it at rest. You can also have us manage your keys for you if you like. You could use our key management system, KMS, if you want. If you want absolute control of your keys, you can use a hybrid security module, because a lot of banks have experience of HSM, so they want to keep using them, so you can. So just by that, S3 is going to meet quite a lot of your PCI goals, your PCI requirements. And it's also obviously a very highly scalable system, so not so much in the storage, because we always do say it's unlimited storage, which is basically keep pumping it full of data, we will keep up. That's pretty much the tenet behind S3. You won't fill it, but by all means try. We're quite happy to take your data. But the scalability aspect is more of the bandwidth of getting data out of S3 in the first place. So if you have a large instance and you have an S3 endpoint set up in your VPCs, you'll be able to pump upwards of 5 gigabits a second on the large instances per instance. The NAT gateway itself, or the S3 endpoint itself, isn't going to limit you. It's just your servers. How fast can they drag data out of S3? We'll cope. And that's what we're trying to achieve with S3. It's also quite well integrated with lots of other services. So the machine learning one, for example, if you want to actually get it to read the data out of S3, you literally just point at your bucket holding your exabyte of data. And that's all you have to do. You don't worry about moving that data around from one place to the other, constantly recycling it 4 or 5, 10, 50,000 times through the algorithms until it actually does train. We'll just do all that for you. You simply just say, my data's there. Please train. And that's really all you have to do. So from a data scientist perspective, S3 is awesome, because it just holds everything they ever need. EMR. So a lot of the ML systems we actually see out there, a lot of them are based on the Hadoop ecosystem. And we've talked about a few of these before at reInvent. There was one good session last year on the recommendation engine for one of our customers. They were all basing that on Spark ML on basically Hadoop clusters running in EMR. Great. So we use EMR because it is basically a fully managed system. And again, one of the things we talk to data scientists, we can take the Hadoop ecosystem infrastructure away from you. You just tell us what tools you want to use. We'll put them on the distribution and we'll carry on. And that is just like music to their ears, because it's just 101 less things for them to actually worry about. So if you want to use a lot of the Apache tools on EMR, you can. If you want to put on a MapReduce, you want to put on Spark, Presto, Zeppelin, Pig, Hive, all the others, you can. And once it's actually in there, you can write any code you like using those tools that you're used to actually do stuff. And if you want to use things that are commercial, such as MapR, then feel free, install that. It will work. Now, it's built to be elastic as well, so as more work comes in on those peak days, you can actually add more nodes to the cluster on the fly, and we can do more processing on the fly. When that traffic calms down, you can scale down that fleet and just not have so many servers again, which is really powerful. And again, the recent change to EC2 as well, where we're now doing per second billing rather than by the hour billing, means you can scale up and down these fleets as and when jobs come in and just not worry particularly about the cost, because this should make things even more cost effective. Now, here's an example EMR cluster. You've probably seen all these. So anyone familiar with EMR know that you'll have master nodes and slave nodes. So with our master node, which every cluster has to have, we will have the name service sat there running on, excuse me, for the HDFS server on the name node, and we'll have the Yarn Resource Manager running as well. There is only one main EMR node or master node. So if you want more nodes, if you want your slaves, we have those. So we've extended the concept of slave nodes to be basically data nodes, which is kind of these ones. These store data on local database systems. So they have HDFS generally installed. They'll get their jobs given to them by the resource managers, and things will just run quite cheerfully. But we also have a system called task nodes. The task nodes are just compute. They can't actually store anything locally, not really, not for persistence. They take the data off of S3, do the processing that the Yarn job told them to do, and they'll send it back to S3, get the next job, and then they'll carry on. Now, these things are much more attractive because they really are just doing that one job: get the data, process, write results, get the data, process, write results. If they die for some reason, if they fall over, all you really have to worry about is that the node manager or the resource manager knows what's gone on, and they can reassign that job to another node. You don't actually have to worry about data loss because they're not holding any. All the actual data is hopefully stored in S3. But these are linked quite intimately to the spot market as well. So the slave nodes can be built at spot price. If you want, rather than paying 20 cents an hour for a certain node, you can pay, well, 2, 3, 4. It's much more appealing on using a spot market bid, and scale out the task nodes like that. So a lot of customers doing overnight processing, for example, not so much this one, they will launch a cluster of like 1,000 nodes at the spot price, knowing that by the morning, well, they may have lost a couple, but they don't care, because they're just data nodes. I'm sorry, just task nodes. So they haven't lost any data if they lose any services when the spot price goes up or they start losing some. So if you are doing any sort of burst type processing on EMR, we recommend you use slave, the task nodes and spot, because it's just going to make your life so much cheaper, which is what people like. So the application is actually available on EMR. If you've used EMR, if you've used Hadoop, they are pretty much all there. Now, the example I'm going to be talking about, that particular company, they were using, as it says, their SparkFlint and Apex as their main sort of processing type systems. That's what they were used to. So that's what they wanted to use. On the database side, they used HBase Hive, and things also use Apache Ignite, which isn't on the diagram, as an in-memory sort of grid database. But I'll talk about those later. For analytics, you can use, again, anything you like. You can use our built-in analytic tools on S3 if you want to. You can use Athena or QuickSight on those tools if you wanted to. But this customer would quite like Zeppelin, they quite like Mahout and Pig, so we installed them, and that's what they used. So it doesn't really matter. Anything that you're familiar with in the Hadoop ecosystem, you can just use. And we're happy for you to use it. And if you want to use our native tools, fine, great. If you want to install anything from Apache or open source or commercial distributions, yeah, install it. It should work. And in the end, we get to slide 34, we finally mentioned machine learning service itself. And this is actually a key part of the system, because in the end, this is what's going to be doing a lot of the learning behind the scenes for your fraud detection system. So the benefit of this for the data scientist is there's no clusters to set up, there's no sizing to actually be done at all. All they have to do really is work out what the data is, how the data is going to work, how the data is going to be managed, why the data is important or not. As far as the machine learning system itself, in terms of nodes, they've got no visibility whatsoever of what we build behind the scenes, because it doesn't actually matter. We'll build what we think we need to actually process and learn and build models on that data. I think most would do know this. This was actually came from one of the actual machine learning projects within Amazon.com. So they actually use this internally themselves anyway, and it's just something we productionized. This was released about 2 years ago. So it's very powerful, and it's actually used by us. And we think everyone should really use it. So what our machine learning service does, it is a supervised learning system. So the 3 things it can actually do, the first one is binary classification. You give it as many training data rows as you like, and it will try and come up with a machine learning model that basically says yes, no, true, false. That's pretty much it. So if the thing you're trying to learn is a spam filter for email, you give in lots of mails, you give it some reasons or metrics why to describe it, and it will decide whether it's spam or not. Nice and simple. If it says yes, you move it to the spam folder. If it says no, you leave it in the inbox. Straightforward. So anything that's a yes, no answer, it can do really well. The second type is multi-class classification. So this is where you know what it is. You know that this data is describing an animal of some sort in this example, but what kind of animal? So you'll have information about sort of the length, the size, the type of skin it has, the paws, the claws. All the information goes into the model, and it decides that's a cat, that's a rabbit, that's a dog. Again, for machine learning, for our fraud detection story, you could also have definitions of lots of different fraud systems or attack vectors that come into the banks normally and decide what kind of fraud was this. And again, you could push your output from your fraud detection algorithm back into a second model and say, what was it? That's a sort of secondary requirement. The first one is, was it fraud or not? That's it. That's a quickie important one, but for later, you might want to know what it was. So second models can be good for classification. The third one really is regression. This is where you basically come up with a continuous number, sort of, that gives you a confidence factor that this item matches the output we think it is. We think this is fraud to 99.3%. This is fraud at 46%, so let's probably can that one and not use it. So getting the confidence factors is sometimes more useful than just getting a yes, no, especially when you feed this into a second model or a third model to do other work. That yes, no is a bit of a binary 0-1 clamp, but it's not really good for further algorithms. But the regression version is actually much more useful going forward. So what ML also lets you do, it lets you get a visualization of what your data actually is. So the data scientist, they can go on screen and basically say, my data source is here in S3. Or they can say it's in this RDS database or this Redshift database, because they hold a lot of data as well. But all they have to do is put it in there and press basically go, and they can start learning on the model. But they can start looking at the data once it's ingested. So these files can be quite big. So as most data scientists will know, when you're looking at yes-no kinds of questions, it's usually quite skewed depending on your subject matter. So hopefully for banks, fraud is no, will be the left-hand column with most of the input, and fraud is yes, hopefully the right-hand column, which is quite small. And sometimes when it can get very, very overwhelming when it's very, very large, 99.999% of the data is one side than the other. So data scientists have to get involved and just look at the data and try and find, well, which data sets make sense, which columns make sense, which ones can I squash together or compartmentalize together, which ones I just ignore because they're not relevant. Right? The street address of the store isn't relevant, say, but maybe the postcode is. Who knows? That's a data scientist's job. So they get to pick that model, and these visualization tools lets them do it. It also lets you classify the data. It gives you a good crack at it. So this first line actually mentions that the data in this particular row says basically cellular or telephone, so that's basically cell phones or fixed line. And that, in the end, is a binary value. So some systems will take these text values you give it and actually use that text string as part of the training algorithm. Well, why? It's just a 1 and 0 in the end. So you get the way of looking at the data, deciding what kind of graph it is, how it looks, and again, that can influence the data scientist's decision. And he doesn't have to load it all into spreadsheets and try and do lots of pivot tables on it. We just ask the model, so I've given you this data set. What is it? What does it look like? Help. And it will tell you. Give them lots of information about classifications. They can then see how the categories themselves are distributed. So a lot of these visualizations are just built in, and it's really good for the data scientist to work out what am I playing with. And it does help them. Another key aspect of ML, it must be better than flipping a coin. As fraud detection goes, that's not very good. If you don't like the hat someone's wearing, that doesn't make them fraudulent. Might have been in the old days, but not these days. So we give you tools to evaluate the model. So for banks, well, in this case, it's showing you on the left-hand side, the grey bars is what really is negative, and the red hash is false negatives. On the other side, it's the same with positives. So when it comes to fraud detection, you want to know, is your model good? Is it giving you an 80% hit rate? 90, 95, 99, that's what you want. But the false readings can be quite bad. So for a bank, you might decide actually a false positive is better than a negative. A false positive gives me an angry customer on holiday who can't use their debit card. Okay, they'll go over it, they'll take some cash out of the ATM, and we'll realize actually they're on holiday, and okay, we'll let them have some money. False negative is they've got your money, they've committed fraud, and they are gone. So with the machine learning model, you can literally slide that bar that's in the middle, and it can impact the model training parameters, and you can decide, actually, I want more false negatives or more false positives. Take your pick, and you can decide for yourself which one is more palatable. You can't say, I want none, because that just isn't going to happen. Because these things do generalize, they do make rules behind the scenes for neural nets, so there's always going to be something that doesn't quite hit that 1 and 0. It's going to be very close, but you're never going to quite get that perfect match. And if you did, I'd actually question your input data as being too perfect. If you can't generalize your input data and it's just too perfect, it's not much use. It's good for today's data and not much else. This also lets you quantify the negatives and false negatives. So you can actually look at this and say, on the daily run, I reckon I might miss 0.03% of the actual fraudulent traffic, and that will actually go through. So you can actually start getting some numerical values and empirical evidence that says, actually, this fraud detection system cost me $500,000 a year. We're going to save $50 million of fraud. Maybe $500,000 will get through. And this can actually help you decide, where is that monetary value going to be? Where is it going to lie? You can look at distributions of the residuals of where your result was based on what the target result should have been. So some of your results might be quite good, some might be quite bad. You can see how the categories got recognized. So you can look down your results set that comes out of the model and say, actually, the blue ones are good, where I was expecting a 4. We actually got the 4 most of the time. We got some close values sometimes, but not all the time. And you can start tweaking the model parameters again to say, well, that's not good enough. I want more blue, less amber. But you have to be slightly realistic when all you're looking for is a yes/no answer. Interestingly, you can also compare models. So when your data scientist has his perfect tool, absolutely wonderful model that's doing brilliantly, the next day it's performing badly. So they can then create another model based on yesterday's input data, yesterday's trained model, and compare it against yesterday's model. And they can start comparing and contrasting them to say, actually, this doesn't work anymore. This data is not important now. This data now is. So let's change the model and play with it and compare against yesterday. And when you can start doing that quite a lot of times during the day, you can really get really good, really fast models out there in the field to protect the bank. So, yeah. I talked about this in detail now, so let's draw some pictures. But first of all, I'm not talking about the actual data sets the banks actually have for the fraud. So, first one is you, the customer, who's all very trusting, I'm sure, never done anything wrong ever. Banks have information on a lot of customers. Let's say you're a global bank, you've got 50 million customers. That's not unusual. You may have information for them for 50 years. They may be doing 10 to 15, 20 transactions every single day. That's a lot of data on each and every one of us. So that customer profile gets quite important. So it includes demographic information, how you shop, where you shop, what your spending patterns look like, your value type of shopping, all that information, that's all there in your customer profile. And banks will often look at up to 3,000 or 4,000 different attributes or input data items for their training sets. And this stuff does build up quite fast. Once you know about you, we get information about the store, so we need to know about that particular store's profile, its security risk profile. For instance, petrol station forecourts are treated slightly more risky than a sort of full bricks and mortar store, just because that's just the nature of that business. Which is why all the petrol pumps now have chip and pin, not just swipe for petrol, because that was so fraudulent it was silly. So that's one that's gone away. And also such things like some places won't be expecting to have £1,000, £5,000 charges. You go to a petrol station and swipe for £1,000, that's probably fraudulent. You go to a coffee shop and swipe for several hundred, probably fraudulent. So again, the store profile gets quite important too, and what sort of things should we expect to see from these terminals? So these two data sets are huge. In the end, there's also the transaction details. That's really small, 1 or 2K maybe. That's all you get. You don't need much. You need the transaction information about the value, the store location, the terminal ID, the long card number, expiry date. Was it chip and pin? Was it swiped? Was it entered by the keyboard? Was it a web-based transaction? That's actually tiny. So the transaction itself is kind of not irrelevant, but it's not as important as the profit information on us and on the stores themselves. That's so much more important to decide, is this transaction fraudulent? Because in the end, if you just swipe £50 off your card, what does that actually mean? It all depends on the context of where it is, the rate of transactions, where you're doing it, why you're doing it. That's when the fraudulent detection actually kicks in and becomes useful. Oh, so let's build one. First things first, I'm sorry to say, is PCI compliance, just to reiterate that. If you're building anything on us for a bank fraud detection system with all the information that isn't PCI DSS compliant, please redesign your system so that it is, because it really has to meet all of these high-level PCI guidelines. They sound very simplistic and very straightforward, and really they're not that hard to achieve. It's very easy to not achieve them as well, unfortunately. So it all talks about encryption of your data, the access rights to your data. Are you managing the patching of your systems and things like that? Is everything logged? That's most of the stuff that's important. Are the firewalls in place to block traffic from the wrong places and things like that? So that's what you want to get in place for all of your systems. If you get this done, and it's not that bad, and just develop within that sort of limited, restricted environment, then you can get a PCI system really easily. First thing first, you may have a data center already, almost certainly if you're a bank. There's very few that are just born in the cloud, but they're starting to appear. So these will probably hold most of your old systems with the tons and tons of data. And they're generating all the analytics you want, and hopefully throwing it back to Amazon, basically on direct connect links, nice big fiber links. You could do it on the VPN, but the VPNs, well, they're not going to be as fast as multiple 10 gig direct connect links. And if you're a bank, yeah, that's what you're going to have in place. Most banks we generally work with will have 2 or 4 direct connect ports put in place just because they need the bandwidth, they need the resiliency. They don't want to have one channel that might fall over. They don't want to just trust one direct connect location in case that falls over. So they'll have double capacity everywhere to make sure they can get that stuff through. Once you're in, you've got access to S3 because you can use a public VIF to get straight into S3 over direct connect and start pumping up your data. and get it into the S3 data lake, essentially. So those hundreds of terabytes, petabytes, or even exabytes. Because S3 is pretty easy to make PCI DSS compliant, it's the right place to put it. IAM can actually be used to restrict access to all the systems, so it can predict who can do which API calls, who can do what where. That's very powerful. I can't do much detail on that because it's probably a session or two in its own right. But with the right IAM controls in place, you can basically make sure the right restrictions are in place for people to get out your system or not. Other services that are very useful, CloudWatch, Config, and CloudTrail. CloudWatch because that lets you monitor the system, which is another PCI requirement. You've got monitoring alarms and dashboards coming in place. Config because one requirement is make sure your security groups are good, they're well defined, they're not opening up holes to the internet they shouldn't, like port 22 to the internet. It's always a good when we see that. It can actually spot those happening and remediate them automatically using Lambda functions. That's what config is really for. And CloudTrail because that's got the forensic evidence of every API call ever done on your platform. It can't be stressed enough that every SAI I've met, every ProServe person I've met, every TAM who deals with other customers, one of the first questions they always ask is CloudTrail turned on? Please turn it on if it isn't. Because when a breach does happen, when something does happen to your account, all the APIs will be in your CloudTrail logs, everything that was ever done by anyone. Without that information, yeah, you're going to have a hard time potentially proving anything. So please just turn it on. And last one is KMS, which is what we use to store the encryption keys. Again, you control the sort of rotation policies. You control which services can access those keys. That's all nice and safe and secure. I won't put Cloud HSM on here, but again, that's an option if that's what you want to do. Some banks have compliance reasons they must use an HSM at a certain FIPS compliance level. That's fine. We have them if you want to do it. Moving on, we have a VPC. Most of you may know this. You may not know a VPC itself is a fully segregated layer 2 network as far as PCI is concerned. So if you have a VPC without any internet access, then no one can get into your VPC. And more to the point, you can't get out. So the data can't leak from your VPC either. But as far as PCI is concerned, that's it. Your network is compliant within the walls of that VPC. You don't actually have to do anything else. They talk about encryption and fly in and out of your environment, but they don't worry about it when you're actually inside. So if you don't have any internet access to your account, actually that's a really simple thing to get PCI compliance. If you do, which this does later on, then you have to do other things. So you build your VPC, you can put the subnets in the VPC as you see fit. It's down to you where you put them, how big you make them, which is easy to use, which security groups you use, we don't really mind. It's all down to your architects, your designers. And then it gets interesting. So this particular platform was built around Hadoop-based tools. That's what this bank in the US was using. So they wanted to use EMR and HBase for Apache as a database layer. Excuse me. They used Spark to actually process the transactions as they came into the EMR cluster. So that's what did the initial processing. And it used H2O as well, which is quite a nice thing. They can basically create Java objects, essentially, and sort of drop them in to the Hadoop infrastructure, so the objects get called when you're doing certain things. We'll talk about it afterwards. So it lets you do Java object calling inline in EMR. It's quite fun. And then these get imported into Hadoop. Ignite was used as a low latency data grade, because if you're trying to read back from databases of any sort, no matter what they are, you're going to be onto a loser just from the time point of view. So Ignite was used to get everything basically in memory, low latency. That's what you want to do. So once you have your models, your machine learning models done and written, it's quite a nice idea to store them somewhere so you can use them again, or possibly copy them to different environments, go from dev to test to staging, etc., into production. So databases are handy, and of course, you need that. You've got to have a machine learning as well there to actually do that particular training. So this is all just for learning. This isn't the inline system that's used going forward for the actual fraud detection. But it could be. It's quite. If you have done this using automation for building, whether you use Terraform, CloudFormation, doesn't really matter. If you've got some sort of templating engine to build this out, you can build it out again. Because what data scientists suffer sometimes on premise is they've got a small test system for development. They think they can catch fraud with a few tens of thousands of bits of data, maybe 1 million if they're having a good day. And does it scale to 1 billion a day? Well, maybe, maybe not. And sometimes you get that sort of fear of it's just not. Yeah, it's just not going to scale up enough when it gets to production. But using the CloudFormation templates or that we have for this sort of thing, you can just build a second environment. It's a copy. The S3 data is still in S3. Both environments can use it. It's not a problem. So data scientists love it. Within a minute of getting something working, they can get it into production if they want to. So go to the animation for, the implementation for this. First of all, we're going to introduce outside factors, unfortunately. We're going to have people like TSYS, First Data, JP Morgan, that kind of stuff. They're going to be sending you transaction data into your VPC. That then has PCI implications because, well, that's outside parties coming over the internet. That's just bad. That's just wrong. We can't do that. So what they would normally do is create a VPN tunnel instead, straight into your environment. So there has to be a dedicated link. You get IPsec on top of that, so you get encryption in the link. It's a private link essentially because you've got one end of the endpoint, they've got the other. So hopefully, if you've got the controls on your VPN connection as well, and PCI DSS should come with that. We've just got to make sure that your processor will actually do it. So data ingestion, they went into Kafka. Of course, you could use Kinesis there if you wanted to, but this particular bank actually had a lot of Kafka experience, so it's a case of, well, you may as well use the experience and keep with it. So they want to get this working quickly, so we're quite happy to help them support doing that. And once it got into Kafka, it basically got streamed into the platform using things like Apex, which is what this bank liked. That then got enriched with all the data using the Apache Ignite, so that's where it takes your transaction data and starts overlaying all the store profile data, all the user profile data, and kept it going all the way into the machine learning model. And that's when it got the result back. So the machine learning check didn't take long at all, but really from the VPN to get all the way through that, to get to the machine learning model, it's got to be quick. And so that's why the Ignite for the in-memory stuff was actually used, because it was the only way to get that latency down. So hopefully, falling wind and nothing going on with the environment, 50, 60 milliseconds, we get a response back from this. So outcomes of the solution. First thing, the cost plummeted. This environment could actually handle 1 billion transactions per day using basically 20 M410 XRH machines. That's all. So the non-prod environment and the prod environments, that's basically $20,000 a month. So they went from 100K with their existing systems to 10K for just prod. And that was a huge drop in cost. So that cost per transaction, I said at the start, is vital. Well, knocking it down by 90% was a good thing for that particular bank. Of course, they spent some of that straight away on second environments to allow them to do more modeling and more training to actually get that fraud bill even lower in terms of what fraud gets through. So they took this as an opportunity to reinvest some of that money to make what they were doing even better, which is a good thing. Speed. So they could now actually take the development system, and as the data from yesterday got processed and added to the model, they could build up the next model and just keep going, keep feeding, keep training. And if today's model training session looked better than yesterday's, we'll promote that to production and carry on with it. If it didn't, we'll wait till the next day's data, and then carry on. And the last one was the resources. The data scientists now no longer cared about anything to do with EC2 instances, what was on them. They were just saying, I want to use Zeppelin Pig, Hive, Mahout, go. And that was all they had to worry about. And for them, that was great. But it's just the tip of the iceberg. This is now in production. It's running nicely. It's saving them an absolute heap on fraud. But they're not complacent. They want to make it, well, possibly even cheaper, but actually more extensible. So the plan they have for the future of this environment, they may well remove Kafka and replace it with Kinesis, because the way that environment works, Kinesis is probably going to be cheaper, but that's just a migration piece they have to think about. But some of the other pieces they may drop in, drop out, and they're having a few trials. But what they think they could make work is make the whole thing serverless, more or less because they can. And EMR is great, does all that processing that they're doing, but as they get more and more experience of doing that processing, they've got the idea of actually most of this stuff could just become API gateway calls from the outside third parties over the same VPN links. We could use not just one Lambda function, obviously a whole suite of Lambda to do that processing that EMR was doing, because that processing is now, quite well defined. It's quite fixed. We know exactly what's going on, so why not Lambdaize it? And then we can use DynamoDB for tracking things, RDS still for holding the model, and then use the machine learning model as before. So this isn't in production, but it's something that the bank is actually looking for, because they think it will, again, save them quite a lot of money. So that's a summary of the journey for this US bank to build this fraud detection system. The ML aspect of it was so straightforward, it was so out of the box for our Amazon machine learning service that they used it. The hard part was getting the historical data in such a state they could actually apply it to the transaction in flight. Take that real-time transaction data, overlay the user profiles, customer profiles, store profiles, and just keep it going as fast as possible into the ML engine. And that's what the whole thing was about. And for that, it was a great success. So thank you very much. That's the end of the actual talk. So we have 10 minutes now for a few questions. Yes, first question.
So we've essentially moved from binary state classification to confidence levels. Is the bank thinking about doing deep learning, stochastic gradient descent, right, on those
Okay, so the question was, is this bank going to move from, say, the binary model they're doing now to the more statistical gradient descent type methods? That's fine. They probably are. They know that this has got, on the surface, the fraud detection is quite simplistic, and they want to do a lot more with it. So they know that if they go into a deep learning system again, they start using more like decision trees, etc., behind things. That will give them a much more powerful solution. But the brief for this essentially was, we just need to do fraud detection, yes, no, then what? So essentially they have this money released to do other projects, and deep learning will be one of them, to see, now we've got this, what else can we do? And it's so much more powerful. ML has its good points and bad points, but it is a supervised learning algorithm. If your problem doesn't suit that, which not everything does, then we have to look at something else. So with that, we're into deep learning, we're into MXNet and things like that for them to actually do it. And they will be looking at that. Thank you. Yes, sir? Yeah. Well, the question was, in the architecture, we looked like the future will replace EMR with Lambda, so is it going to be used at the training stage? The idea is to use that to replace EMR's job of overlaying that data and taking all the aggregate stuff we have from on-premise, all the historical data, all the stuff about store profiles, user profiles, and inject that onto the transaction as it's in flight, and then push it into the machine learning. So the ML model is still going to do most of the actual learning itself. But it's just there to say, EMR is doing all this crunching now, and it's great, but as we get more of a strong view on what's actually happened with the data, we think we can do it in Lambda. So if they make it work, I'll be back next year maybe to talk about it, but we'll see how that actually goes. We're going to have lots of challenges just moving all that stuff into Lambda anyway. But it's a fun project for them, I guess. I wouldn't mind doing it.
Sorry, are you planning to implement more models under the hood in the machine learning module?
Yeah.
Sorry, because I've noticed that like one of them has this, for example, logistic regression.
Yeah, the machine learning team are working hard to basically expand the profile. I think Ian talked about recognition earlier. That was one of the ones that came out last year. And so they're looking at releasing more services, but there's nothing I can unfortunately share with you now. But a lot of customers have actually asked for a lot more unsupervised learning techniques. So I'm sure these things will come in time, but I'm afraid there's nothing we can share at this point. There is actually things on AWS or Amazon.com. There's a quick start section, which you can look into some of these things, especially with things like PCI DSS compliance. We'll have some quick start things to say, here's your landing zone, your initial environment. So that's pretty good. So if you just want to get a basic PCI environment, nothing in it, but it's built, secured, etc., and it's there ready as an empty shell, look at Amazon.com/quickstart, and it's there, and you'll find it on there. That's a very good way of getting started. So the PCI stuff it does sound scary, because if you break it, then your bank is in trouble. But it's actually quite easy to do on our side. It's not that complicated. So that quick start guy will actually give you everything you need to get that up and running from a standing start. Okay, I think we're out of questions. So thank you very much for your time. So hope you enjoy the rest of the Loft. Thank you.